Hello everyone, and you're very welcome to our Culture Night event, Tyndall Talks Science Snippets. In today's short session, we hope to give you a very brief overview of some of the areas that we work on here at Tyndall National Institute. The schedule today will consist of two short 10-minute presentations. The first will be delivered by Dr. Patrick Morrissey, who's going to give you an overview of the photonics work that we carry out here at the Institute. This will be followed up by PhD student Ardeshir, who's from the Life Science Interface Group. Ardeshir will be demonstrating a bioimpedance measurement system. We hope you enjoy your time with us during the short session. And without further ado, I would like to introduce you to our first speaker, Dr. Patrick Morrissey.
Hello, my name is Dr. Patrick Morrissey, and I'm the Centre Manager for the Photonics Centre in Tyndall National Institute, but also for the Irish Photonic Integration Centre, or IPIC. IPIC is based in Tyndall, but also across many of the other universities across Ireland. And I'm going to talk to you a small bit about how we're building the future through our technology and also through our trainees who are becoming the future research leaders across the globe. So first of all, what is light? Well, most of you will be fully aware of what light is, but you'll be thinking of light in the perspective of what the visible spectrum, which we see here in the bottom part of the graph, and that is the light we all know about because we see it every day. But also, there's a significant amount of the spectrum. Most of the spectrum is invisible to us. So we have shorter wavelengths, which have more energy, and that's on the right-hand side there, which is things like ultraviolet light and X-rays. And then we also have much longer frequencies or wavelengths, and they're on the left-hand side, which are infrared light, the whole way down to radio and broadcasting. But the bit we're going to focus on today is more what you see in the middle there. It's the visible light spectrum, and a small bit outside of that going into the near infrared. So let's look inside the technology. So the technology we're talking about here is how we generate, transmit, and sense light. And so within Tyndall, we fabricate devices. These are very small devices at the semiconductor scale, which is typically down to the micron scale or smaller, the whole way up to building systems that might be centimeters of scale. So what do we mean by micron? Well, if you look at the graphs or the pictures on the bottom of the graph there, on the left-hand side, we see what are called micro-LEDs. These are very small LED structures, and the width of them is about 10 microns. And to put into perspective, the width of a human hair is about 100 microns. So each of those micro-LEDs is about a tenth the width of a human hair. So we're talking about tiny structures, so small that you can't see them. And what we do with these devices is many things. So they enable the backbone of the internet, which I'll talk about a small bit later. And also we're developing them for micro-LED displays for things like augmented reality. These are products that are going to hit the marketplace in the next couple of years and beyond. And then we also use them in areas such as medical devices. And again, we have a couple of examples of what they are going forward as we speak. But to bring you into our world, it's very much about these very tiny, complicated structures, most of which are so small you can't see them, but we integrate them together into full-scale devices that you can hold in your hand and use. So first of all, looking outside of our technology to the outside world, one of the things we do is connect the world together, and which is enabling the recording that I'm doing here, and in particular, how we transmit this across to you in Ireland or outside of Ireland. So if we take a look at a journey here, so on the top left, I'm recording a video. It's being recorded through electrical signals and being stored on my laptop, but then I need to communicate it. And in the communication, which can be across the globe, then what we're doing here is we're converting the electrical signals into optical signals, and we're putting them into optical fibers. And most of you would be aware of what an optical fiber is. It's a very tiny glass fiber where we push light through it. And the good thing is that that light can travel over long distances before the signal is deteriorated and it needs to be boosted. There are many of these optical fibers around the world, and you can see there in the middle one such map which shows how there's a heavy amount of connection across Europe, between continents, etc. And what we can do, and why light is so important to be able to make this happen, is that each color or frequency of light can carry data. So when we put loads of colors together and we squeeze them into one fiber, we can increase the bandwidth, or we can put in more and more data through the one single fiber. So when we try to download a gigabit of data, a movie, then that can be done in a matter of seconds, and we're not waiting hours for that data to come across to us. So the key part of that technology is the semiconductor technology on the left-hand side, such as lasers, where we convert the technology into optical signals. And at the receiver side, we have a detector that converts that optical signal back to electrical signal, so the individual on the far side can read it. So let's look at a different area, and this is about wearables technologies. And here we're using very much the same technology, a technology that's called, in many cases, silicon photonics, and we're using it for sensing. And you'll be very familiar these days with wearable devices where we can sense things like your blood oxygenation level. And that's enabled through an optical sensor, a sensor that's built into the watch or wearable device you're wearing. However, it has limited applications. And so what we are doing now in our laboratories is using more complicated sensing systems to increase the information we can extract from them. These are fantastic technologies because they're small, so we can use them in wearable devices. They are non-invasive, so they sit outside the skin and they can monitor you continuously. And also they can gain a lot of sophisticated data. And that's the bit we're working on now. So in the future, we can have devices such as the one shown here, where we can also measure biomarkers. So we can get the state of health of the individual, and we can track people in real time. So this is going to move us a step ahead of where the technology sits today. And we're doing that not just ourselves, but with most of our research, we're doing it with the best companies in the world. And one example here is Rockley Photonics. They're a company pioneering this technology, and they're here in Tyndall with us, where they employ a number of their scientists and engineers and building their team out, which is great for us because it's shown that we're not only delivering impact across the globe through our technology, but we're also creating economic impact here in Ireland and creating new high-value jobs. Rockley is a great company because they've just listed in the stock exchange with a valuation that's over $1 billion. And also there's a lot of talk that this technology that we helped co-create with them, will be in future Apple Watches. So this is the best technology in the world that we're developing that's been deployed right across the world. The final example I'm going to give is very much in the same direction, but it's around moving from wearable devices into medical technologies. And one example here is where we're trying to use a similar type of technology, but to accurately measure the fetal stress levels in mom. So here, again, the compact nature of the technology, the non-invasive nature of technology is hugely important. So we believe, and we haven't done this yet, but we're working on it, that it will be possible for us to measure the fetal stress level, the stress levels from outside mom safely and continuously. And what this will allow clinicians to do is to make better decisions with mom and with baby. And in particular here, we're trying to support WHO's goal to reduce the mortality ratio. And that's one of the advantages of our technology as well, is that not only can it be very effective, but also it can potentially be low cost and be deployable right across the world, which is hugely important to us. This is a technology we haven't built yet, but we're working it heavily in our laboratories, and we hope it is something that we can achieve in the next couple of years. So it's more about our facilities, and unfortunately, the objective of the night tonight, Culture Night, is to bring you into the building. And we've had many years where we've brought the general public into the building, and there's a significant wow factor. You can see the main entrance hall in the center there, and it's a fantastic facility. And not only is it a great place to come and visit, but also you see there on the left-hand side, we have a glass wall where you can see into a real semiconductor fabrication facility. And there are very few places in the world where you can do that. Unfortunately, it can't happen this year, but we hope to welcome you in next year and give you a chance to see those facilities, to meet some of our researchers you see there. And of course, this is the building that the Queen visited when she did come to Ireland. It was her last place of visit before she headed off. And so we talked to her about the future of technology and how Ireland is pushing that agenda forward. And we hope to be able to do that with you in the next couple of years. And finally, I'm going to mention a small bit about people. So it is really about people. A key part of our program here is to train PhD level students and above that. And what we're finding today is that the demand for our trainees is huge from the whole way across the globe. And these is from the best technology companies also. So it's an exciting opportunity for people to come in, to train up, to make an impact through technology. And technologies that, such as photovoltaics, that help address the global climate address changes, from to healthcare devices, and we can be hugely impactful, not only here, but when they move on to their careers after Tyndall. So we very much welcome you to join Tyndall at some point in the future if you have an interest in this space, and hopefully we'll see you at some point. Nice to speak to you.
Thank you, Patrick. Next up, we will be visiting PhD student Ardeshir from the Life Science Interface Lab to learn all about bioimpedance measurements.
My name is Ardeshir and I am working on designing a bioimpedance measurement system for bladder monitoring. I am a PhD student working in Life Science Interface Group. If I want to give you a quick introduction about bioimpedance measurement and bioimpedance itself, bioimpedance is the response of a living organism to an externally applied signal. So what that means is that if you have a tissue or any living organism that you are trying to detect some sort of biological event, then you can apply a signal to that, and based on the material and characteristics of that tissue or living organism, then you're able to detect a change on the signal that you are recording. So this actually can help to diagnose different, for example, diseases, which I will talk about. And that's actually something similar to when you are trying to detect or monitor your heart signal, your heart rate, because heart produces an electrical signal and you are able to connect electrodes to it and record that signal and the change of the voltage. So a quick introduction of why I'm working on bladder monitoring, especially for elder people or older people. What happens is there is a common problem which is called urinary incontinence, which is when the person or that patient is not able to control their bladder. And what happens is the time that their bladder is full and involuntary leakage or void will happen, and the person suddenly releases the urine and they don't have control over their bladder. So this can be embarrassing. And imagine that, for example, paraplegic patients, they don't have control over their bladder as well because there are some neural damage to their body or to their spine, so they're not able to control the urine flow as well. So what happens here is that if there was an indicator that could be connected as a wearable device to their body, and it would be able to tell them that at this moment your bladder is going to be full, so you need to take necessary action, for example void it or connect, put or insert catheter to your body, then that would be very good, because then they would avoid any unnecessary infection, for example for catheter, or they could avoid the problems for sudden release when you're in public, for example for older people. So this would be very helpful. Bioimpedance measurement is very good for that because it's a non-invasive method, and as I said, it has various applications. One of the other applications is that, for example, you can detect a breast cancer with that. So imagine these electrodes, you connect them to your body, and you apply a signal based on the frequency, and you are trying to measure or detect some sort of signal change based on the frequency. and you're able to send that data to a smart device, and with some sort of algorithm, then you can actually turn these signals that you've recorded to some sort of image that shows the inside of the body, and for example, it can tell you if there's a tumor inside your breast or not. Another application is for cell measurement. So you have a bioimpedance measurement device here, and you have your cell, for example, coming in to a tube, entering from a tube, and then you have your electrodes, and then you're applying your signal, and then you measure the voltage change based on the type of the cells. So if the cell is cancerous, then for example, you're able to tell the change in the impedance, and you're able to kind of categorize and say, okay, this is a healthy cell or it's not a healthy cell. If you can look at this, actually this is how we model a cell or a living tissue. So, and based on that, you can see that the cell is can be modeled with resistors and capacitors. And if you apply a signal to that, then you're able to record a different signal based on the frequency that you're applying the signal to. So imagine that as a cell as a series of resistors and capacitors that they can be conductive, and you can apply current to them or voltage to them, and you're able to record some sort of signal change. So for a bioimpedance measurement device that I'm designing, you're looking at a simplified block diagram of that. We have a impedance measurement device here. This is actually an LCR meter, but it's able to you're able to measure the impedance with that. So quickly, we have a signal generator inside this, and this signal generator generates a signal based on the amplitude and some sort of parameters that you give it to the device, and then it applies the signal over this root with 2 electrodes, and then you measure the change with these 2 electrodes, let's say. So we have 2 electrodes here for applying the signal, and we have 2 electrodes for measuring the voltage. And you, based on that, you apply the signal, and then you measure the voltage, and voltage over the current will give you the impedance that you're looking for. And this could be any tissue or any device or any other thing. So as I said, we have a impedance, an impedance LCR meter that is able to measure the impedance. We have an oscilloscope here that I have connected to a series of very simple resistors, and I have a capacitor here as well. So at lower frequencies, what happens is if these are just resistors, you are able to see the number or the impedance that you're looking at. So I have put a 30 ohm resistor there, and as you can see, with the frequency of 1K, it shows 29 ohms. So if I increase the frequency a bit, it goes to, let's say 2 kilohertz, we still see the same thing. So the resistors, they don't, the amplitude of the impedance or the resistor do not change with the frequency. So if you change the frequency over a range of frequency, that resistor, the number that you can see here doesn't change, and it's going to be actually fixed and constant. And if I actually increase the frequency again, let's go to 10K, 100K, as you can see, it's pretty much fixed. There is a very slight change because of some parasitic parameters that are going on onto that board, but the range should be, the number should be fixed. It doesn't change that much. So let's go back to the original 1K, and as I said, we have a 30 ohm resistor here. You're actually able to see the voltage, that's, as I mentioned, that we apply voltage. So this line here, this orange line here, is the voltage that is applied, and this green voltage is the voltage that we are able to detect if the impedance changes. So when I increase the frequency again, you can see that nothing happens, and the amplitude stays the same, but just you're seeing that the frequency is being increased. So let's go back again to OMK. The moment that I connect this capacitor to the circuit, you could see a drop into the voltage, into that voltage, and also now you are able to actually see, if I increase the frequency now, you should be able to see a drop into that number. So let me just, okay, yeah. So now you can see actually that the voltage here dropped as well, and the number here from 289 is dropped to 14 now at 100K. So if I increase it a little bit more, you can see that it's decreasing again, decreasing again, decreasing again. So and this is because of that capacitor. So if we imagine, or if we, as I showed here, the cells and the body as a bunch of resistors and capacitors, based on what is going on, or what any biological events that is happening. For example, your heart is pumping blood to one of your limbs, and you're trying to measure the blood flow, or as I said, detecting the cancer based on the value of the resistors and capacitors, which we model that as a biological tissue. Then based on that, you should be able to detect, and based on some algorithms, you should be able to say that we have, for example, a cancerous tissue, or in my case, I'm working on bladder monitoring. You should be able to say that the change happened, and for example, the level of the urine is raised, and you should be able to say that for the people who have this problem, urinary incontinence problem, to go and avoid their bladder. This is a big device, so what I'm trying to do is to make one of these boards. This is called PCB, printed circuit board, and I'm trying to make this into a very small board. Of course, this has lots of options which we don't need for a wearable device, but I'm trying to design something like that, and we solder the components on this. And this is a soldering iron, and this is actually a camera that we have that helps us solder. So that was a brief and quick review of my work. I hope you enjoyed it, and best of luck with all of it. Thank you.
Thank you, Ardeshir. That brings us to the close of our very short snippet view of the work that we carry out here in Tyndall. We hope you enjoy your time with us. If you would like to know more about the research that we carry out here at the Institute, please visit www.tyndall.ie. Thank you for your time.